Let's start that one. Okay, got that. All right, so like I said, guys, before, motors are 30 to 40% of every electrical load in every building. So wherever you go, you guys gonna be stuck with dealing with motors. That's why we harass you with a couple of lectures about motors. This is probably the third, the fourth time you guys have heard about motors, especially the ones, even Derek, where you guys did motors one whole semester. So keep in mind that's the probably third, fourth time, and the last time they're going to hear about motors, except Matt. So motors are motor controller, big deal. So a few things, guys, I want to focus on. Determine machine layout in an industrial project. I want to remind you that we are following an industrial project. And Matt, if you look at here, every single one of these MDs, MCs, these are machines laid out and connected to the bus stop. So this project is following the book is following a project, and all these see all these machines on the manufacturing floor laid out in the manufacturing floor connected to the bus stop. Okay, why do we care about the machines? Because they have motors. Describe the types of motors that we're going to have from DC into AC to synchronous in the industrial project. Operation of the type of motors. How do they do operation of the types of motors? Motor controllers. How do the motor controllers from across the line? They call them across the line, guys. Easy one into the VFDs, and then motor branch circuits installation. We talked a lot about branch circuit and sizing and what's not. So these are a few things that we will be guys talking about in this chapter. There's a little formula. You guys have seen this one, Karen. You've seen it before. The amps. When you hit the amps, that's full load amp of a motor. Is when you calculate the amp of a motor, you take the horsepower of a motor. You guys have done that with us. Multiplied by 746. That's the equivalent of 1 horsepower. And then divided by the voltage. And if it's three-phase, you divide by 1.73. You have to account for the efficiency and the power factor. So that's the full load current of a motor coming from a mechanical horsepower. Mechanical horsepower. I don't know if you guys understand when what the motors are. If you have a of course I can't erase on that one. Motors, my friend, you bring to them electrical energy, right? And you get out of them mechanical energy. That's probably the beauty of the motors. You get electrical energy in them, and out of them, what do you get? Mechanical energy. You heat, cool the building, you ventilate the building, you cut through 2x4s, and so forth. So this formula, please be aware of the formula. This will give you the full load current based on the horsepower, the mechanical horsepower for your system. This is a couple of motor types, guys, and electrical symbols that we use for motor types. I want to highlight a few things. This is armature. We use this one you're going to see for DC motors. We're going to be using these in particular for VFDs, conversion. We talked yesterday, guys, about the coil and energizing the coil. Transformer, we control transformer, big deal. We talked yesterday, guys, about normally open, normally closed contact. These are probably, and we talked about also stop buttons, the fuse symbols, the overload symbols. All these are circuit breaker symbols and resistors, how to put resistors and field coils for the DC. So these are a few symbols when it comes to the motors that you should be familiar with. Like I said, Karen, dealing with controller motors is like learning a new language. If you don't know the alphabet, you can't talk or you cannot read it. Am I making sense, Matt? Makes sense? Okay, so be aware of that one. A single speed squirrel cage induction motor. Induction motors, Derek, are the heart of the whole machines. Almost every machine that you deal with, not almost, most of the machines have induction motors. Induction motors are low maintenance, very low maintenance. Very simple. They have a cover, they have a bunch of bars made out of typically aluminum and sometimes copper. Run around the rotor starting coil. So you have a coil around and you have a bunch of bars here running right through it. So that's your induction motor. It has a good starting torque, so we use it a lot for starting. Likely by common magnetic circuits, it's the stator and the rotor are coupled or linked together through magnetism. So here's how it goes, guys. Here's the coil here, here's the rotor. You energize the coil, it induces voltage into the rotor. The induced voltage create induced current. The induced current create magnetic field. And the magnetic, like north and south, the poles will interface between the stator and the rotor to get you the spinning when it comes to the motor. So that's kind of the magic about it. Right from here, Karen, you bring the voltage. Here's my three-phase 480. My three-phase 480 volt. You bring it in here. Then you create a magnetic field. You induce voltage into the rotor. The induced voltage will create induced current. The induced current will create north and south. And you have also on the stator north and south. And these two poles will start pulling away from each other. Same thing. And what this will give you rotation into the stator, into the rotor or the shaft. Any comments, guys? Any questions about how an induction motor works? Very, very simple. I don't know if when you were in high school, Matt, if you guys did a motor, really very easy. You have a coil, make a coil and put a screw or something inside it and put a voltage there, and you almost got yourself almost a motor. That's really as easy as it gets. Not a whole lot. That's why people love these. They're low maintenance, very, very low maintenance, the induction motors. Can I get you to understand, guys, the key word when it comes to designing systems is induction motors. Induction motors. That's my induction motors. The reason why we use Aram motors, the main reason for using motors, guys, is to get us torque. That's it. Mechanical energy. Mechanical energy. Or work. Mechanical energy. Otherwise, we wouldn't be talking about motors. We'll be talking about lights, right? When we put electricity through a lighting fixture, guys, we get light energy, right? We get light. We can see. When you put energy, electrical energy into a machine, a motor, you get mechanical energy. Now, what do you do with the mechanical energy, Karen? Do you cut the 2x4? Do you drill in a hole? Do you heat and cool your building? Do you pump the water and the gas and what's not? It's up to you to do. Do you make it in an assembly line where you can make a car? So that's the most important thing about motors. Can I get you guys thumbs up, Chad? Torque. We understand the motors are associated with torque. What's a torque? The spinning force. So that's how do you find the torque? You take the horsepower of your motor, multiply by this magic number 5252 and divide it by the RPM, the speed of a motor. That will get you, gentlemen and ladies, or ladies and gentlemen, that will get you a torque of a motor. Adam, if you're a mechanical engineer, will be your baby, the torque. You take that torque and you go design your machines based on that torque and the horsepower. Any comments, guys? Any questions about the torque? So the spinning happens because of the interaction between the magnetic field of the stator and the rotor to get you the spinning mechanism. So remember this formula. In the industrial project that we have, Karen, you guys are looking at it right here. You just can I get you all these machines. Here's all the machine types that we have. When you look at them, guys, there's say ME and MC. Here's how many of them we have of each type. Here's a description of each one of these machines from the engine, from vertical drills and what's not. Number of motors. Okay, so number of machines, number of motors, same thing here. Number of motors of this type, as well as the horsepower of every one of these types that we have. Every one of these types that we have. So number of machines. Why do we have the number of machines twice? Well, we have number of machines twice. Number of machines, number of motors. I see. There's the machine and the motor. Sometimes some certain machines have more motors. Like look at that. ME has 18 motors for ME. So some machines have more than one motors. But here's the horsepower. Okay, so some machines have 1 horsepower, 1 motor, Adam. The others have multiple motors. So that's the motors that we have in our plant. So just a couple of description. Number of motors, 6 3-phase motor driven, the 6 ventilating blowers. This is just description of what we have. 10 2 horsepower motors for the fan cool and what's not. So list of squirrel cage, single phase. These are the single phase ones that we do. And the first one where of course, all of these are single phase. I think these are 3-phase. Anyway, so these are the list of the motors that we have in this plant, single phase and 3-phase. Any comments, guys, about the list of the motors? Comments, questions? trying to get, okay, single phase. Okay, so moving on into 4-speed squirrel cage motors. When it comes to the motor, Adam, we need to power them and we need to control them. Powering is easy. Fuse, conductor, overload, and you bring that motor. Then controlling them, you can either control them manually, guys, turning them on and off. You can reverse them. You can speed them up, speed them down, and sometimes you need to speed control them. So when you speed control them, guys, some in the old days, before VFDs, they used to have different windings, so they can control the speed differently. So they have certain machines that has two windings that can give you 4 speeds. Speeds are obtained by changing the number of poles. By changing the number of poles, guys, N is the speed equal 120 times mass frequency divided by number of poles. So poles. So Adam, if you change the number of poles in the machine, you change the speed of a machine. That's how they used to do it, and still change the speed of machine so it can give you speed 1, speed 2, speed 3. Who cares? I always say who cares? Guys, machines are doing a mechanical function. If the mechanical function requires speed control, speed change, you need to be able, you can't just run it at full speed. It will cut right through your equipment. It will damage your equipment. You need to slow it down. So speed control becomes on the motor is a big deal. So here's one way of doing speed control. Let me go directly to show you guys that one, speed control for that motor. Where am I here, Chad? Here you go. We talked about this one, talked about that. Here's the spinning. Can you guys see where the north and, here's my north and south, oops, it's my north and south spinning. So you have magnetic field induced right into the rotor. And you have north and south poles next to it. What happens if you put the north and north next to each other? They pull away from each other. That's the principle of operation of induction motor. Spinning of the magnetic field will make the rotor spin. I wanted to go directly into this one. Okay, speed control, multi-speed. So you have a motor like this, guys. You can see they have multiple windings, and based on the winding that they connect, they can get you different speed forward or reverse. So for example, Adam, I can, if I connect this arm, if I put this arm right here, I am getting 800. If I put the arm right here, 1200, 900, 600, all forward. If I want to reverse that motor, I can move that direction and reverse that motor for 600, I believe 900 where it's located. So this is by changing the number of coils. Does it make sense, guys? Changing the number of coils connection, it will change the and the polarity and the phases. It can change the forward and reverse. Can I have thumbs up, Chad? We know how to change the speed of a motor by changing the windings, all the windings. So if you have, this is one way of changing the speed by have different windings and connecting them. Make sense? Yes? No? So that's basically what this is, changing the speeds of a motor by changing the windings. If you guys look at your book, inside your book, it will tell you that these are 4-speed, 2-winding induction motors. 4-speed, 2-winding induction motors. You can get 4 speeds. You can have 600 forward and reverse. You can have reverse 600, forward 600, 900, 1200, 1800 by connecting them. If you look at page 133, gives you the connection. So that's what I wanted to show you in terms of speed control. So the first thing you need to know about speed control, Adam, is you can speed control a machine by having different windings. Can I have thumbs up, Chad? Different windings that connect them. That's it. You guys, do you remember when we were doing a schedule last semester, and when you were picking the mechanical schedule and says the controller 2-winding, 2-speed? Anybody remember that? And I told you this is one of the NEMAs that gets you change the, you can have multiple windings based on the windings that you connect to get you different speed. So be aware that's changing the number of poles, which is basically the connection of the winding, will get you different speeds. Okay. The second thing that we'll talk about, so that's speed control. The second thing that we would like to talk about, guys, is primary resistor starting. They call it resistors. If you have a 50 horsepower Karen, and you start the 50 horsepower like this, you grab that and you turn it on. Put it on here. You you turn it on like this, you know what's going to happen? It's going to suck so much energy because of the inrush, and the light in your building will dim. The light in your building will dim. So the smarter than Chad guys use something called primary resistor. So the primary resistors do a very simple thing. If the voltage is 480 here, 480 volt, when you energize, you close these contacts. So now I will cut the voltage up to here, to the motor, say 240, momentarily. Can you see that? Because the leftover will be right across 240 right here. So I'll take, say, 240 volt across the resistor and 240 here for a total of 480. So they cut the voltage, say, by half. By cutting the voltage by half, they cut the inrush. The inrush current will be cut. The inrush current will be cut down. And by cutting the inrush current, guys, they will reduce the mechanical and electrical impact on the machines. Who cares? When you start your motor, your machine's not going to jerk, right, and bust the windings and everything else. That's called resistor starting, or voltage reduction resistor starting. Here's the control system for it, guys. You close this one, this energize, this will close. Now the motor's up and running for 10 seconds. This happened for 10 seconds. There's a timer here. You guys went through the Derek. You went through it with Scott. You use timer. The timer here times for 10 seconds. After 10 seconds, it times out, closes this contact. When it closes this contact, this R really closes, and then bam, 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 it will shunt the resistor, and the voltage here goes all the way to 480. So for close to 10 seconds, guys, you reduce the voltage. By reducing the voltage, you reduce the inrush. Who cares? What's the inrush? The current. Who cares? The question always, who cares? That will reduce, your light will not dim, your circuit breaker will not trip, your mechanical equipment, if you're a conveyor, imagine a conveyor and you crank the motor and the motor, bam, pull everything else. It's going to jerk the machines, right? What happens if you keep jerking a machine? It'll bust it. So by doing it this way, and they reduce the mechanical, they call it mechanical and electrical impact on the motor. That's called voltage reduction. Voltage reduction at the start. This is not speed control, voltage reduction. That's one method of voltage reduction. The other method of voltage reduction, Karen, is using an auto transformer. Same principle, gentlemen. Close this contact, energize that baby. Now, bam, bam, bam. These will go, and these also will go. Now, the voltage was 480 here. I'm going to drop it down to 240. My inrush, inrush was, let's just say I'm going to say 600 amp. I dropped it down from 600 amp by cutting it into, let's just say 200 amp, right? That's more manageable. We dropped the inrush. My machines, the power system doesn't see it. No light dimming when you start the air handling unit, right? And your mechanical equipment will not be jerked around and damage the bearings and the belts on the machines and what's not. Then after that, after a while, guys, what happens is the timer times out. Here's the timer, 10 seconds. When this times out, this will close, this contact will energize, and bam, 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 we will shunt, basically drop this transformer out of picture, and we go back into our 480 volt with full load current of this motor to get us the full speed and full torque. Any comments, guys? Any questions? I know through review, you guys, this should be a review for you. The ones who went through I hope so. The ones who went through our semester, because I taught this one in the electrician program myself. And Scott, you guys have done this job. This job and the job before, Adam, you have done it in our lab. You are the one that is suffering a little bit. But these job, guys, we've done them in our lab. So I hope it's a review for you. Otherwise, we spend, Dunwoody, we spend one whole semester, guys, 12 weeks on motors. So, and we throw you guys in them in the first semester. So I hope you understand. I'm not going too fast on them because you have seen them before. Okay. Then there's something called wound rotor motor. So these two methods, guys, are called voltage reduction start. Voltage reduction start. Wound rotor motor, it's like induction motors, except they have some windings. They have some windings in the rotor. The rotor has some windings. And they use them to get more torque out of them. So if you have a press, punch presses, they typically use these, gives you more torque. Induction motor. The magnetic field principle, the same thing as a motor. Have a three-phase windings in the stator, and also the rotor has windings. The rotor has windings in it. I don't know if we have a picture of it. There is secondary resistor. We'll talk about these. Punch press. There's secondary resistors, guys, to control the speed. Speed selection. We have 3 sections delay when speed is increased, and no delay when speed is not increased. Used to bring the motor up to speed smoothly. This is how it looks like. Let's go directly into that boy. Okay, so let me see directly into my, we got these. Okay, here's what we call it, wound rotor motor, guys. Wound rotor motor, what they have windings in the coil, and they have a bunch of resistors that they connect to the rotor through a brush, the brushes and slip rings right in here. And the power will come 480 volt come right in here. And then when you connect them, it looks something like this. Okay, so here's what they do, guys. By connecting, that's the topic of motors is, so you get your 480 here, you get your 480 volt here, and by controlling the current that in the rotor, is the stator, by controlling the current that going right through, guys, the rotor, they control them by all these resistors, right? The more resistor they put in the circuit, the slower the motor will be. So connecting at A result in the first and low speed operation, second speed operation, and third or high speed operation. By connecting them, guys, so we're connecting at A result in the first or low speed connection. We're connecting here. So if you leave it as is, you got yourself the lows. Then you close these. Here's the second speed. You close these. You get your third speed and the fastest. Here's a way of getting 3 speeds out of motor and also starting your motor with a reduction in the inrush. Guys, for motors, Adam, there are 2 things you have to know from an operation point of view. You need to be able to start the motor with a very low inrush so it doesn't damage the machines. And you need to speed control the motor. Here's a place where you can speed control the motor and reduce the inrush. It's through a specially designed motor called wound rotor motor. Now, 3 of you guys have wired this in a lab. I hope so, Derek. When you put the slip rings there, so 3 of you guys should have wired that one with us in our lab. So what is it? It's a specially designed motor where you can connect resistors to the rotor right in there. Okay, why do we use it? It gives you more oomph as you bunch holes in sheet metal. You need a lot of oomph. This is a good motor to get you oomph more than the induction motor and speed control. So that's, baby, will get you there. Okay, this is the control circuit for it, guys, and I'm not gonna go through. We wire it. Very easy control, not easy, but it's good control circuit by selecting which speed you want. Can you guys see the first speed here, the second speed that you want to run it at, and the third speed? Based on these speeds, the first speed will get you as is. Second speed will close, bam, bam, close these. Third speed will close these. You know, so these contact. When you close them, guys, you shunt. If you close these, what happened here? If you close it here, all these are gone. So you have an induction motor. So this is the controller for an induction motor, a controller for an induction motor. Any comments, guys? Any questions? Any comments? Any questions? I know it's a little bit involved with the speed control. You basically controlling, there's a lot of timers to make and controls and timers and control relays to make sure that the system works. Slow it down a little bit as you speed it up. You have a delay for the speeding to make sure the system is going to work properly. Any comments, any questions, guys, about wound rotor motor controller? And all this, in this section here, this is called your controller. That's your controller. All this junk inside it. Comments, questions, guys, about this controller? Any comments, any questions? Derek, do you remember putzing around with these guys in the lab? The controller. This is exactly the one that you guys have in our lab. The exact one. You guys should have wired it. Now remember, we're not control engineers, but if you are, we can be control designers too. It's really not rocket science. But I don't walk you step by step through that one because you should have done that one through the. But it's really, it's not rocket science. You close this one, and then you start closing and opening contacts and what's not. But the bottom line is you close this and you control these contacts right in here. Which one to open and which one to close to get you the speed that you desire. So that's my wound rotor motor. Who cares about wound rotor motor, gentlemen? Wound rotor motor will get you a special characteristics that an induction motor will not. As in high starting torque and making holes, like we said, punch press motors and so forth. It gives you, it has a better characteristics than an induction motor. Okay. Now so that's the second baby that we're going to do. There's another thing, guys. We talked about these. This is the determining direction of rotation for three-phase motors. Three-phase motors, you can change the direction of rotation, Karen, by changing phase A and phase C. Any two phases. If you flip them, you get yourself, instead of an exhaust fan, instead of exhausting all the fumes out, now you're pulling air in. Or if it's a pump, and instead of pumping the water out, you're pumping the water in. Don't you think it's a disaster? Can you guys see it's a disaster? If your motor, do you see what the disaster? If your motor, if you flip these wires, you're an engineer, you're in the field, and they're going to hook up this motor. The first thing you should be scared when they're hooking up these air handling units is, oh, is the rotation right? Are we supposed to rotate clockwise or counterclockwise? How are we going to check that? To make sure that they're not, you know what happened if you have an air handling unit and instead of pulling out the air, you're pulling it in. There are stories of all these big dots guys got sucked in and damaged. So I'm gonna let you know, guys, it's a disaster. You got to determine the direction of the rotation. Is it forward or reverse? Okay, are we pulling this way or that way? Anyway, the smarter than Chad have something called, thanks God, phase rotation, guys. The phase rotation, if you wanna, the first thing you do is you connect it to the motor. You connect this phase rotation to the motor, and if the indicator goes this way, so and you rotate the motor. If you want the motor to go this way, you know where the motor wants to go because you're the owner. I want it to go this way, and you connect this machine to it. It will give an indicator this way, right? Cool, we're done. Now we know where it should go. Then you hook him up here. Then you hook these back here to the source, and you see, and this indicator should go to the direction that you want it to go. If it doesn't, Karen, you go and change any of these two phases. So they use this machine, guys, to define the rotation of the machine. First, you know where the machine is going to be rotating. Connect it to the machine rotator. It's going this way. Then you go connect the lines to the line side right in here. And if it gives you the same rotation, good. If it doesn't, just flip two phases. Right? Instead of connecting this line to here, you connect this line to here, to B. So that's your rotation. Rotation connection. The same thing, let me go as long as I'm on it and the rotation, guys. I'm going through these two because they have nice pictures. So we talked about these, we talked about the rotation. Can you guys see that, how they do the rotation? First they go to the motor and they check the rotation of the motor. Look at this. So first you connect it to the motor. Now you know which phase rotation going which way, and then you go connect it to, can you guys see, connected to the load. If it gives you the same indicator forward, if you want your motor to go forward, when you connect it to the motor, it says forward. Cool. Now unhook it up and hook it up to the surface, to the panel. If it says, yeah, forward, great. If it doesn't, all what you have to do is just flip these. So how am I going to flip that? I'm going to flip phase A. I'm going to take phase A here and phase C here. Done. Then it should show you the same rotation. Okay, so that's if it's connecting to the source. Now what happened, Adam, if we have an existing service and we need an existing service and we need to find the polarity. Which phase is this? Is this phase A, B, C? That's how A, B, C. I want to find which one is in this A, B, C here. Same, that phase rotation, they're connected to this side. This side will say ABC. Give you an indicator here that it's ABC. You will connect, I don't know if it's, we have another picture that connect them to the other side. Here you go. Then you connect them to the other side. It should give you the same indication. If it doesn't, if it gives you the same indication, then it becomes A, B, C. Say if it didn't give you the same indication, right? Then very easy. This becomes C, B, A. Done. You label them C, B, A, and you run. Why it's so important, guys? Because if the system was ABC and you hook it up to a system that's CBA, now guess what? All your machines in your building start rotating the other direction. Screw up all your machines. I don't know if you guys see the gravity of this. So it's a big, big deal. Phase rotation. Who cares? When you guys are project managers, that's what you're going to be paying attention to, right? You're electrical designers, project managers. Do you want to sit there? You're in charge of project manager and you have no clue what a phase rotation is. So when you become there, you learn more about it. That's an introduction. So these are the tools that you need when you go into the field. You're not going to be using them, but you're going to be a project manager there and see what the heck. So before we connect them, oh, maybe let's do. I heard Chad talking about phase rotation. Let's go check the phases of these systems before we learn the wrong way, right? And damage certain equipment. Okay. So that's basically what I want to talk about. The second thing, guys, motors, three-phase motors in the US come with 9 leads. They call them 9 leads. Derek and everybody else, you guys have done these with us. We have 9 leads. When we do 9 leads, they're labeled, as you guys can see, they're labeled from here 1, 2, 3, 4, 5, 6, 7, 8, 9. And they always come like this, a 1. 1, here's how the Y comes. And when you label them, you go clockwise from the top to the bottom, you label them this way. Okay, that's the labeling. Then if you want to connect them, the delta, the same thing for the delta, guys. Delta comes this way by manufacturer. Comes like I always say 3 corners. That's how delta comes. And they're numbered exactly like you said, from 1, 2, 3, 4, 5, 6. You move all the way to 7. I went to 4. I skipped out. Here's 5, 4, 5, 6, 7, 8, 9. And then this is how we label them if they're not labeled. Luckily, guys, you're not electricians. If you're an electrician, when I teach the exam prep, we drill the people how to label these. Because they test you on that. That's how they label them. Who cares about labeling them? Because based on labeling them, Adam, we can connect them high voltage or low voltage. We can connect them high voltage or low voltage. So this motor can be connected for 480 volt or can be connected to 240 volt. The last thing you want to go, if you connect this motor this way, they call them series. Can you guys see? Connect here and connect these here and connect these here. You bring your phases here. This is called a high voltage. For high voltage, this is the voltage. This is how if you connect them this way, you have to bring the 480 here. If you bring the 240, Karen, you will get smoke out of your motor. Literally smoke. So that's the connection, and you can see how the connection. These are always on the nameplate, guys. So you know. If you connect them this way, if it's a delta high, that's if a delta or Y. The motor has to be either delta or Y. Typically, most of them are Y. But if it's a delta, the same thing, guys. Here's a 40. Here's a 480. Here's a 480 volt, 240 volt, 3-phase motor. Looking at this one, this is called high voltage. And Matt, if you know it now and you read it now, when you go to the semester that talks about motor, you're going to be flying, because those guys wired it. So we connect these two here, and it gets you a whole high voltage. So I have to bring this voltage into L1, L2, L3. Does that make sense, guys? High voltage, low voltage. The smarter than Chad, Karen, they make motors with 2 voltages and 2 types, either delta or Y. Y is the more dominant. If it's first delta or Y, and we know how they come in delta Y, the shapes. 3 corners, 1, 2, 3 at the top, or a Y like this and a one coil above it. Then the way you connect them, if you put them in series, put the coils in series like this, can you see in series here? Get your high voltage. Now, how do you make it low voltage? I'm going to go directly. Here's how they make them low voltage. Same thing, Adam. If you're looking at the same motor, this is a Y motor. If you're tying this motor, here's my 480. If you're paralleling the coils, can you guys see how they're connected? We're paralleling the coils. If you parallel the coils like this, gentlemen, you get yourself a lower voltage, which is the 480. So you have the 240. If you don't put 240 across this coil, you will burn this coil. So that's your low voltage connection for a Y. For a delta, guys, and here's the Y connection. For delta, here's my delta. Can you guys see the same thing? Here's my delta low voltage. Here's my 240 low voltage. These are my low voltage, low voltage, low voltage. Here's my low voltage. So these are the connection that you can have for low voltage. Any comments, guys? Any questions? Comments, questions? So here's the connection. There's some motors come with 12 leads. Then you have to connect the, if you were to connect them here, you have to connect these two together to make them a Y. If they're 12 leads, and you connect these two to make them a delta, and you apply the same rules. You apply the same rules. Okay, I know it is. Any comments, guys? Any questions about dual voltage, three-phase delta and Y motors? Please read this one. A lot of you guys are review for that one, so I'm going to go directly. We talked about, can you guys see how labeling them? Go clockwise from top to bottom, both Y and delta. The most important thing I always say, guys, is to remember how they come in three pieces. They come in three pieces, right? Here's one piece, two, three pieces here, and these come in four pieces. One piece, two pieces. Each one of these is a coil. And they must be labeled this way. If you don't label them, you're in trouble. Okay. Now moving into, this is a three-phase. We talked about Y and delta, high voltage and low voltage. In the single phase, guys, the same thing. There's something called split phase motor, tied motor. Adam, you wired it many times with us. A lot of you guys wired it in our labs. You can have high voltage operation or low voltage operation. You can high voltage or low voltage operation based on how you connect them. When you connect high voltage, here's the connection, guys, for clockwise and counterclockwise. We'll talk about. Let me go directly before into a couple of pictures here because they're really easier. If you have single phase motor, Adam, your single phase motor comes in two sets of coils. They're always labeled the following. They're labeled T1, T2, T3, T4, and T5, T6, T7, T8. These are called the starting. These are called the run. For single phase motor, guys, you have to create a phase shift in order to get the motor to start. So they have a starting winding. Okay, so that's four winding. If you guys want to connect these in high voltage, very easy. Tie these two together, and here, and you bring your voltage here, 240. Done. Very easy. You series the coils together. So that's, here you go. You're looking at it right here, how they connected to 240 or 230. That's the connection of high voltage for a single phase motor. I know a lot of you guys are designers, but the more, like I said, the more you know about this, the better designer you will be. So these are high voltage. You series them. If you want to put them low voltage, look how they put them all in parallel. Matt, remember, if this coil is 120 and this coil is 120, if you put them together, they add up to each other, like series. 240. If you parallel them like this, you get 120, still get the 120. That's the principle for the coil, guys. Like when you put resistors in series with us and all this good stuff. So that will get you, can you guys see that you parallel them, you put them all the odds together here, all the evens together on one side, you get yourself a lower voltage. You get yourself a lower voltage. So most of the motor guys have only one winding like this instead of two start windings, one winding. Then you go 5 and 6. So if you want to connect the motor 5 and 6, so if you want to go, here's start winding, run winding. Here's how you connect them, guys. If it's only one winding, you just take 5 and 8 and you put them across T and T1. If you want to reverse the motor, the same thing if it's low voltage. If you want to reverse the motor, reversing the motor, let me go directly to this one. If you want to reverse the motor, Adam, all what you have to do is just make this one T5, T8, and make this one T5. How do you make this? How do you make this T5 and T8? What I'm saying, gentlemen, is you grab this wire from here, that wire, and you bring it here, and that wire, and you bring it here. Now your motor was clockwise, it's going to be counterclockwise. That's how you reverse a single-phase motor. How do you reverse a single-phase motor? By reversing T5 and T8. How do you reverse a three-phase motor? By reversing any two phases. Any two phases. Any comments, guys? Any questions? Now, what happened if you, in a single-phase, guys, if you come, here's my, in this case, my 240. This is high voltage 240. If you bring the hot here and the neutral here, the motor will run in one direction. If you bring the hot here and the neutral here, the motor will continue to run in the same direction in a single-phase motor. If it was a three-phase motor, there's no neutral. If you flip the phases, the motor will go the other direction. So in single-phase motor, you don't have to worry about where the neutral is located in which side, all right? But you really have to go disconnecting internally in order to reverse it. And we have a couple of methods, guys, of reversing three-phase motor. Okay, so that's the connection that come clockwise and counterclockwise. Let's go a little bit on, okay. So that's talking a little bit, guys, about single-phase motor, connecting them and what's not. I want to talk a little bit about DC motor, and then I'm going to give you a quick break. DC motor, guys, they work on DC, right? So these are how the first motor to be invented are the DC motors, because DC came before AC. When Tesla came here and invented AC for the rest of us, guys, and we moved to the AC and the war between Tesla and Edison, right? So you guys hear about the current, the war current and what's not. So all the motors at the beginning, they were invented DC. So in a DC motor, guys, you bring DC here through brushes. Oops. You bring the DC. Look at the DC motor. Very easy, not easy, but you bring the DC right in here, okay? And here's my 240 volt DC motor. And then you inject the voltage right into the rotor, into my rotor, and you create basically a magnetic field by injecting the voltage directly into the rotor. So here's how it looks like when you do them. This is your rotor, or they call it armature, and there's a field, of course, there's a coil. There's different ways of connecting them. This is called short shunt connection. This is long shunt connection. Who cares? Without getting into too much details, how many of you guys have DeWalt? If you have DeWalt, go to the section that has about motors if you want to learn more about them, and you learn about the characteristics in each and every one of them in terms of starting torque, running torque, speed control. So each one of these guys have different characteristics of speed control. DC motors are awesome for speed control. That's why they use them. The more voltage you put across them, Karen, the more speed you get out of them. That's why we like them. But the way we connect them is this way. There's series field and shunt field. Can you guess that? And all these are connected together, and you bring the voltage across them, positive, negative. There's also cumulative compound motor. This is how they connected, and differential motor. Can I just get you, without getting you guys too much hung up on the DC, can I get you to understand one little thing? The way you connect it will decide the torque coming out of this motor, the speed control for this motor, and the proper application for this motor. Did you guys hear me? So there is, without getting into, if you need more details about which one applies for which, please consult, DeWalt has really good short description, each one of them, when you reach them. But be aware of that one. Okay, if you have DC motors, and which you guys also wire a few of them, they come in the following, guys. The armature come labeled A1 and A2. Adam, this is on the test next week. It will tell you how do you label a DC motor. The armature, which is the rotor, comes as A1, A2. The field, the series field, comes as S1, S2. The shunt field comes as F1, F2. And the accumulating field comma C1 and C2 or S3 or S4. These are how they are labeled, guys. Can you guys see the labeling? Then how you connect them, can you guys see that? How you connect them will decide the characteristics of this three-phase motor. For example, so that's the connection. Look at this one. This is a connection. You take, they put them in series. Can you guys see the connection here? I will bring to your attention, Anna, can you guys so look at this here and look at this? The way the location of A1 and A2 will decide the direction of the DC motor, either clockwise or counterclockwise. So how do you reverse a DC motor, gentlemen? Derek, how do you reverse a DC motor? By flipping A1 and A2. By flipping A1 and A2. Can you guys see that? Look at A1. A2 directions. By flipping A1 and A2 in a DC motor, it will change the direction of that motor, clockwise or counterclockwise. So that's my DC motor. Same thing, guys. Here's my shunt. How you change it by the shunt. Always, Adam, look at the location of A1 and A2 compared to each other. Can you see that? You flip the A1 and A2, that will change the direction on a shunt motor. Compound motor, the same thing. Compound motor, all of them, A1, A2. Okay, any comments, guys? Any questions? Where would we use DC motors? DC motor, guys, used to be popular where you need speed control. Now with VFDs, guys, VFDs have taken the place of all these DC motors, basically. They still have good torque on them and good applications for different industries. Karen, I'm going to give you guys 10 minutes. And I would like to focus on the last thing on this chapter, guys. Talk about the VFDs and conversion, and that's not. And I need your attention about the VFDs. I really do. Shall we take 10 minutes? Thank you. Talking a little bit about the DC supply. Now, Adam, we need DC supplies for two reasons. Now, we've just finished talking about DC motors, and we're going to talk about VFDs, guys. How are you going to go get DC? There are two ways of getting DC, guys. You can either get batteries, huge batteries, right? And you get to a DC source. Obviously, you're not going to do that in an AC world. So what they do is they have a direct current power supply. They convert AC to DC. When you convert AC to DC, guys, convert the AC into, my friend, the DC. There's something called half-wave rectifier. You guys did it in electronics. They're using multiple diodes and different technologies. Diode permits the current to flow in one direction if it's forward or biased, and not in the other direction. The output voltage never reverses direction, direct current. So what they do is they use a diode, guys, without getting into the electronics. Here's one. I'm going to focus on single-phase full wave rectifier, what they call a full wave rectifier. Let's go directly to the single-phase half-wave rectifier first. I don't think I have a picture of it. Let's go here. So come on, Chad. Okay, there you go. So what they do, guys, they use AC source and they rectify it to DC. Very simple, Adam. They use something semiconductor called the diode. The diode blocks the current to go in one direction, not in the other direction. So look at this. So the diode works this way. So it allows it to fire, stop here, fire, stop here. And so your voltage will look something like this. Here's my voltage. That's, believe it or not, Karen, this is some form of a DC. Any comments, guys, about this some form of a DC? You take 120 volt AC here, and this is, I don't know, let's just say blah, blah, blah. Let's just say 110 DC, and a question mark next to it. That's halfway. Now, the smarter than Chad, then they go to a full wave rectification. Full wave rectification. Half-wave rectification, full wave rectification. For the full wave rectification, Adam, there are two methods. Either they use a transformer to do that, tapped from the middle, and this technology, two diodes, or they use a bridge, what they call a bridge. You guys did both of them with us. The outcome is the same. So it goes this way, and when it goes in the other way, guys, it flips it. So it just flips the voltage, so it becomes this way. And believe it or not, Adam, this is, you're looking at a DC. This is a full wave rectification using diodes. And again, I don't want to get into the, the diodes, they direct, they flip the voltage when you go negative, guys, just flip it over, the full wave rectification. So that's another source, and then you put it through a resistor to limit the current and dump it across the load, or the resistor would be your current. If it's three-phase, three-phase half-wave rectification, guys, here's how they do it with three-phase. They use three diodes in every phase, and then they bring the three-phase in here. Can you guys see each one of these phases? And at the end, the voltage will look something like this. Now it start to look as a DC. Can you guys see that? Instead of an AC, everybody knows what a DC, the pure DC looks like a line like this. So now we're getting closer to a DC, three-phase, half-wave, three-phase. The best one, Karen, is the three-phase full-wave rectification, which they use a bridge, multiple diodes like these, 6 of them, and they fire at different voltages. So at the end here, you're looking at, this is my voltage. This is my DC voltage. Now, Matt, does that look like a DC? Just one line? Right? The pure DC looks like this. This is very close to this, right? Compared to an AC. Any comments, guys? Any questions about full wave rectification, single phase and three phase? So that's what all what you have to know is typically all of them are full wave rectification now, single phase or three phase. By doing it this way, guys, they can get you. By doing it this way, they can get you a source of a DC from an AC. So, Karen, if you have a DC motor in a machine in a building, you need to power it. What do you need to ask for? You need to ask for a DC drive. What the heck is a DC drive? It takes the AC 480, for example, and convert it into a DC, let's just say 400 volt. That's it. How does it do that? It takes multiple diodes, semiconductor, like right inside your laptop, and convert them, allow the current to move in one direction, not in the other, and convert it into a DC. Now you can power your DC machines. Can I get you guys to understand the word DC drives? You're going to hear Jerry from Square D and Color Hammer talk about DC drive. You hear them all the time. What the heck is a DC drive? You're looking at a DC drive right here. Taking AC, convert it to DC. Why would we convert it? Because we need to put it right here. This is my DC motor. I'm going to fire and burn my DC motor. Can I have thumbs up, Chad? We understand it, so I can move away from that one. Cool. So that's my DC, my DC drive. So let's go directly into the conversion. So that's how you get the DC source from an AC in this day and age, not from batteries. So this is just talks about how you calculate it, guys, in an average of a voltage. So first you multiply the RMS. Oops. You multiply your RMS by yeah. This is a couple of so you multiply your R. Mine is not doesn't want to work, huh? So for DC, oops, here we go, pointer. All right, here's the pointer. Okay, so here's my RMS, which is 120 volts. Say you multiply it by this number, and then you multiply again by 0.637, and that will get you my DC voltage, the DC voltage for this. With half wave, that's full wave rectification, single phase. Half wave rectification, you divide this number by 2. Is divided by 2. So that will give you the value for calculating the DC output, but typically the drives will have a DC output. Here's your full wave rectification 3-phase. We talked about this one. Then the phase shift control, you need to determine the output of the voltage. Now, Karen, this is your DC drive, basically. So when you talk about DC drive, guys, all these will be part of your DC drive. Can you guys see that? My controller. Here's my controller, and here's my DC motor. And I can control phase shift and current limit control and speed control and what's not. They use these controller, guys, to control the speed of a DC motor. All what you want to ask right now, if you have a DC motor, Matt, one word. You have a DC motor in your machine, you're going to ask for a DC drive. You size the DC drive based on the size of your motor. That's your controller that you use multiple motors. You can control the firing and the voltages. By controlling the voltage, guys, by controlling the voltage here, they can control speed. Just imagine, Matt, having a car that you can control its speed. Can you think about that? Having a car, you can't control the speed of your car. Can you imagine the value of this car is worthless, right? The same thing for a motor. I mean, now worthless. Motors typically, if they have a fan, you just let it run. But imagine the power when you can't control the speed of that motor. Great, you can make it do a lot of stuff for you. Okay, so that's one way of controlling the DC motor. Any comments, my friends? Any questions? Comments, questions? So that's phase shift controller. We talked about this one. That will leave us into now. If you have a DC motor, Adam, you have a DC drive. Now, what happens if you have an AC motor, gentlemen? AC motor, and you need to speed control an AC motor, an induction motor. You ask for an AC drive. Did you hear the word AC drive? If you have a machine, you guys VFDs. That's your VFDs. VFDs control the speed of an AC motor. DC drives control the speed of a DC motor. Does that make sense? And power it. So if you want to control the speed of a motor, an AC motor, guys, VFD is your baby. Okay, DC drives and compare DC drives and DC motors, but less speed, not as controllable, but less expensive and less downtime. So instead of having the best control speed is the DC motor, guys, reduce the voltage, reduce the speed. But the DC motors are high maintenance. There's a lot of work and downtime and whatnot. So with the technology, advancement of technology and power electronics, they start manipulating the AC voltage, guys, to get your DC and AC back again. And that's the principal operation of your VFDs. So it takes frequency apply of the voltage, number of... So in order to control the speed of an AC motor, guys, you have two methods. Either the number of poles or the frequency of applied voltage. So if you guys remember, the speed equal 120 times F, the frequency, divided by number of poles. Now, this is how they control the frequency. If you control the frequency, Karen, of a motor, you will control the speed of that motor. That's welcome to the VFD. So a few things about the VFD, guys. When you control, the problem with the VFD is if you reduce the frequency, you will reduce the impedance of the coils, which increases the current in the coils. Reduces inductive reactance voltage, so that will increase the current. The current will go up. So the smarter than Chad say, hey, here's my frequency. I will reduce the frequency and also at the same time reduce the voltage. By reducing the frequency, guys, and proportionally reducing the voltage, they can control the speed of an AC motor without burning it. Welcome to the VFD. So what does the VFD do for a living? It reduces the voltage and the frequency of a motor to speed control it. Can I hear that, guys? Reduce voltage and frequency to reduce the motor speed. Because if you reduce the voltage only, you will burn your equipment. Okay, Adam, here's how you come with your VFD, gentlemen. You grab a voltage AC output. So let's say this is a 240 output. You convert it, let's just say a 200 volt. A couple of chokes and what's not to control it. You smooth it with a capacitor. Then you come over here. So this is my AC voltage right here. Can you guys see AC voltage? At this point, I have a DC voltage. Then you invert it back at this point, guys. You invert it back into AC again, into different form of AC. Different form of AC by firing all these transistors. By firing all these transistors at different times. You convert. So a VFD does two things, guys. Take AC to DC, control it, and then convert it back to AC. Why would you do that? Why would you do something like this? Why would you take AC instead of AC dumping it to an AC motor? Why would you convert it to DC and invert it back? Because when you convert to AC to DC, you can control the speed. Very simple. So you take the AC here, convert it to DC, control the speed, control the DC up the level of the DC, and then inject it back at a different frequency at different time, guys. And by doing it this way, they can control the speed and the frequency which controls the speed of this motor. That's basically the principle of operation of an AC, of a VFD. Control AC, DC, control it, invert it back at the right frequency and right voltage to control the speed of the motor. They use also silicon-controlled rectifiers. Silicon-controlled rectifiers, guys, the problem with VFDs, these can cause some harmonics. What's harmonics? We talked about harmonics before, guys. Overheat for motor and transformers, blow fuses. So there's some drawback, trip circuit breakers, and some transistors here can be driven into saturation, so it malfunctions and what's not. So these are a few drawbacks of these technologies. Now this of using the first technology, which is SCRs, which is this one. This is called SCRs. These called SCRs right here. So it has drawback. The Smarter Than Chad developed a new technology called the IGBTs. These are all transistors. You did electronic transistors, right? Transistors are, it always amazes me, guys. If you have a very good conductive material, we call it conductor, and we put current into it. If you have a very, very bad conductive material, we call it insulation, and we insulate the conductor with it. And if you have a semiconductor, one that doesn't like to conduct that much, but it does, we call them semiconductor, and we made computers out of them. All the electronic digital world has been made out of semiconductors. One of them is called IGBTs, a transistor. Transistor, bipolar gate, insulated gate, bipolar transistor. Voltage control device, ability to turn on and off very quickly. So it turns it on and off, guys. It cuts that DC to convert it into an AC. There's no slow recovery time, so it has an advantage over SCRs, better than SCRs. And it uses diodes at the beginning to convert. So long story short, how does it look like? We don't have a picture of it. Let's go directly and look at it, how it looks like from here. So go back here, my friends. We got these. Here's my SCRs. This is one technology of using it. When you put SCRs, guys, when you invert the AC, it looks like a square wave like this. It doesn't look sinusoidal wave, it looks a square wave. So here's what happened. You grab a nice AC signal like this, convert it into a DC signal, and then invert it back into this, and dump it across your motor. Your motor, guys, wouldn't see the difference. Okay? Still not good AC. So that's your, and then they have IGBTs. These are the output of IGBTs. So then they can smooth them and make them better, guys, into technologies. Where's the, I want to see, I thought I have a picture of IGBTs. I don't. Oh, shit. Okay, so this is, so if you guys look at these are the outputs, a stepped wave, approximate sine wave. If you put IGBTs, so they start manipulating it, guys. Here's IGBTs. If you put this technology, you convert it back into a, here you go. That's what I'm looking for. So when you put it, this technology, it starts looking like pulsation. So Adam, this looks like something like an AC signal, right? So your motor, when you're driving your motor with VFD, you're not actually putting a sine, you're putting pulsation. Pulse, 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 pulse into the motor. And the motor is dumb enough not to know, and it keeps working. By reducing the pulsation and the distance between these pulsation, guys, you can control the speed of the motor. Don't you think those are smart? With these pulsation, instead of reducing, if you reduce the voltage, you burn the motor, AC. They're making pulses, and they reduce the distance between them and the magnitude and the frequency. They can control the frequency and make the motor much better. Because of all this, guys, it creates heat inside the motor, so they start making the stator core insulation paper in a much better. You have to make a motor, inverter rated motors. They call them inverter rated motors. Inverter rated motors. So that's basically the technology that you're going to be seeing. So I'm going to take my AC, guys, right in here. I'm going to convert it here into DC. I'm going to invert it back here at this level into pulsation. into some type of a pulsation. Some type of pulsation. And dump it across my motor. You're looking at it, gentlemen, right here. Any comments, guys? Any questions about VFDs? VFDs give AC, convert it to DC, invert it back at different pulsation, pulse into and dump it across the motor. In the process, you can speed control that baby. You can speed control that baby. Okay, so that's my VFD, which you guys will hear them all the time. So we talked about the IGBTs, disadvantage fast. So this is just a few things, guys, about advantage and disadvantage of the two technologies. Advantages, disadvantages of IGBTs. Advantage, CR is not used in power supplies, reduce problem with harmonics. IGBTs, these are the IGBTs. So what you're going to be looking at is basically right now is IGBT technology. This one. Disadvantage, fast switching. The disadvantage, this is not just that simple humanity. The disadvantage, guys, the fast switching will create a very high voltage pulsation or spikes that could burn equipment. Okay, so without getting too much, guys, VFDs, we specify them to control the speed of an AC motor, induction motor. What they do is they take AC to DC and invert it back to some form of an AC pulsation. Why do we do that? To speed control of a motor. What's the impact? They create heat inside the motors. So Adam, you're going to hear people at Michelle Cooley Erickson and everywhere else, they will be talking about inverter-rated motors. Inverter-rated motors. The inverter-rated motors, you're going to hear them all the time, guys. Inverter-rated motors, they have the following. They have a separate blower that blows air, continuously blows air onto the motor at different, regardless of the speed. So you cool it. Guys, VFDs create heat inside the motor. So you need to get rid of the heat. So what do? They have a separate blower cooling it. Number one. Number two, they have insulating papers between the windings in the stator cores. So they have more insulation between them. Phase paper added to the terminal leads, better insulation. They make better magnetic wire. Magnetic wire used has a higher grade insulation and the better wire and higher grade insulation. And because of all this, that motor will be bigger than a normal motor. With all this, gentlemen, remember one thing. When you have a VFD and you talk to your mechanical engineers, the mechanical engineers are smart enough now to ask the manufacturer, guys, to specify a so-called inverter-rated motors. So a specially designed motor, fatter, fluffier, more insulation, more cooling, so it can handle all this heat generated by the VFD. Anyway, so that's basically the motor. The VFDs, guys, my VFD can do the following. VFD, they can have low speed torque curve. They can accelerate and decelerate the motor, ramping up or ramping down the motor. You can control the current, the starting current. You can control voltage per hertz, which is speeding it up, speeding it down, maximum hertz, maximum speed, minimum hertz, minimum speed. So these are what the VFDs will do for you. I want to set my minimum speed at 100 RPM and my maximum speed at, say, 1800 RPM, okay? And that's my maximum minimum. I want to set my start current not more than 300 amps on this motor. So you can, all these settings, guys, happen in the VFDs. And then the VFDs will fire all these IGBTs to get you the desired settings that you are looking for. Gentlemen, if you are in the electrical industry and you're specifying right now, most of these HVAC equipment that we use, guys, when we went to Boston Scientific, did you guys see them all over the VFDs? That's what you're looking at. Why would they use them? They ramp the motor up, so, and when you turn it off, they ramp it down instead of up, down, ramp up, ramp down. That will reduce the mechanical and electrical stress on the mechanical and electrical system and speed control it. They can make the fan work. What better than speed control a fan in order to control the temperature in the room? Think about it. Speed controlling a fan, guys, can control temperature in the room. How many times did people complain in offices because it's too hot or too cold? VFDs is one of the solutions. Does that make sense? VFDs is one of the solutions. Speed, slow down, get you more heat, more water, less water. Am I the only one who is excited about that speed control? If you deal with it as much as I do, you're going to feel it. It's a big deal, man. It solves a lot of problems for us, a lot of problems. So that's basically, guys, what I want to have. I know I went through a lot of stuff. We typically, all the stuff, guys, we teach, I bet you in our motors, and like I said, 12 weeks, we teach them with hands-on and component. So that's hopefully will wrap up. For us as a designer, guys, you went through the hands-on, or most of you went through the hands-on part. So that was just recapping what you need to know as a designer. You need to know two things: AC drive for AC motors to control the speed, and DC drive for DC motors to power them and control their speed. And how do they work? We just talked about the controlling their speed. Any comments, gentlemen? Any questions? Comments, questions? So that's, I don't think I forgot any of these stuff here. Let me see here. Here's how the installation, guys, they put more insulation and paper and what's not. Talked about the current goes inside them. It's just a couple of pictures. Here's the phase identifier. A couple of, here's my VFD and the settings that you do for the VFD, guys. I've seen a few of them around. This is just giving you guys a few things about the frequency, the efficiency of a motor is the best when the motor is fully loaded. Can you guys see that? Look at this one, a quarter horsepower. The efficiency, if it's fully loaded, 69. If it's 1/2 load, it's 60. So long story short, remember always to fully load the equipment. These are all the machines that we talked about here and the loads with them. Connections, a couple of connections. And that's basically it. Any comments, gentlemen? Any questions? Comments, questions? It's a big chapter. Please read it. Keep the book if you have it, and you're gonna be dealing with VFDs for a long time. AC drive and DC drive. If you go to Collar Hammer Gears or Square D, there's a whole section about AC and DC drives. Hopefully that will give you an introduction. More to come. This is only 10% of what you need. The rest you guys will fill them as needed. Okay, thank you guys.